Very good morning or good evening, good day, depending on where you are. It's my honor and privilege to introduce Professor David Metalog for today's webinar presentation. As you know, this is this Advanced Air Mobility webinar series started in March, and every month we have one program. And today's presentation is from Dr. David Metalog. Let me say a few words. There is quite a lot of information here, but I will just take 2 minutes, keeping in mind the time limits that we have. Professor Metalog has received his PhD degree in 1995 from University of Virginia. He has nearly 3 decades of experience, both in the industry as well as in academics. And since 2012, I believe, he has been with University of South Carolina. He has been in a number of standards organizations as a member, and more importantly, he is an IEEE fellow. And for his work primarily on channel modeling. And I'm also very proud to be his friend and colleague. We have planned to work on several activities in near future. We started working, and you will see more outcomes very soon. Very specialized knowledge and expert in the field of channel modeling. And I invite Professor Metalog to begin his talk. Thank you.
Thank you, Kamesh. Okay, let's begin. I'd first like to acknowledge the IEEE Vehicular Technology Society for sponsoring this webinar series, and thank Kamesh for organizing this great series of talks. All right, my title is Reliability for Air-to-Ground Communications and AAM. Well, since you're tuned into this webinar, you probably know that there's a lot going on in aviation today with UAVs and drones, still in passenger conventional aviation as well. There's also a lot going on in radio, 5G, 6G, Internet of Things. Aviation communications and navigation and surveillance connects these two. Here's an outline of my talk. I'll begin with an introduction where I'll talk about aviation growth, which is mostly focused on passenger aviation, and that's where most of my data is. But I'll talk a lot about UAS, unmanned aerial systems, also known as UAVs, unmanned aerial vehicles, also known as drones, and focus a little bit of this talk on AAM, advanced air mobility. I'll talk about some reliability and availability concepts as they've been defined generally and in the industry by standards organizations, and zoom in a little bit to AAM, talk about NASA's program in AAM and the associated NARI, which stands for NASA Aeronautics Research Institute, a group of NASA people devoted to advancing aviation. I'll look at air-to-ground communications for the most part, but I'll also talk about air-to-air, and I'll relate this to the terrestrial communications with which many of us are more familiar, cellular and so on. For reliability, I'm going to focus primarily on the physical layer, PHY, and talk about 2 of the primary impairments to physical layer reliability, the air-to-ground channel itself and jamming or interference. I'll briefly discuss adversary perspectives and how that can make us more attuned to keeping our aviation links reliable. And then I'll talk about countermeasures to some of these impairments. And then finally, I'll conclude with some ideas for future work. All right, once again, I'm focusing on passenger aircraft. This graph shows the number of passengers in billions over the last 50 years. As you can see, has increased dramatically. Now, we did see a dip in 2020 due to COVID, and that still hasn't gone up to levels pre-COVID, but the industry expects that to be achieved in the next 1 or 2 years. So we went from 40 million passengers in 1970 to 4.4 billion passengers in 2019. And if one includes, in addition to passenger aviation, all other types, freight, military, and UAS flights, there are over 100,000 flights per day. This plot shows the number of annual plane crash deaths per 10 billion commercial airline passenger miles. And you can see that has gone down dramatically. The graph on the right shows the trends. The number of crash deaths is going down and the number of flights or departures is going up. And this is what regulatory agencies love to see. This is a very safe way of traveling. And we want to maintain these standards for new technologies and applications like AAM. So this gives us a little background perspective. Aircraft and radios. We have to do wireless communications for aircraft, of course. Any mobile platform requires it. And safe aviation, when there's more than a few aircraft in the environment, requires air traffic management, or ATM. In the industry, we refer to ATM using communications, navigation, and surveillance, or CNS, to achieve safe flight, safe and efficient flight. UAS and AAM are new cases, so there's got to be a little bit of research on this. The graphic there is taken from NASA's AAM webpage, and it describes what AAM is about. Basically, to develop an air transportation system for moving both people and cargo between places not previously served. And this can be regional, local, and even urban transportation, which may be one of the most challenging cases. NASA's Aeronautics Research Institute, or NARI, has a number of different working groups focused on advanced air mobility. They have groups on vehicles themselves, on noise and community acceptance of urban and regional aviation. And they also have an airspace working group, which deals with actual flight operations and air traffic management. The graph on the lower right of this slide shows a little bit of a number of things that they're involved with investigating: collision avoidance, separation provision, synchronization of traffic, and so on. Both air-to-ground and air-to-air communications are required. Air-to-air is sometimes referred to as V2V, meaning vehicle to vehicle. This is not to be confused with the common usage in terrestrial car-to-car V2V communications. The graphic there in the lower right is a little small to see, but I will elaborate on that shortly. Now, reliability. What do we mean when we're talking about reliability? Well, this is an adjective, and Merriam-Webster defines it as suitable or fit to be relied on, or synonymously dependable. Wikipedia has an entry that talks about a reliable communication protocol that notifies the sender whether or not the data or message was delivered successfully to the intended recipient. So we're going to use that synonym, dependable. The RTCA, which is the Radio Technical Commission for Aeronautics. This has been the United States aviation standards body for about 90 years, and they're still in operation today. They work on various standards for aviation, civil aviation. C2 stands for command and control. This is sometimes also referred to as CNPC, control and non-payload communication. MOPS is minimum operational performance specifications. In their data link specifications, they define availability, continuity, and integrity. Availability is the probability that the operational transaction supported by the system can be initiated when needed. That is the probability that the link is available when it's needed. Continuity is the probability that the operational transaction supported by the system can be completed within a given transaction expiration time, which is application specific, given that the link was available. Now, these operational transactions are nothing but message transfers: air traffic control, pilot to controller, and so on. Integrity is the probability that the transaction supported by the system is completed with no undetected errors. Well, in traditional communications engineering, we do address availability and integrity. And availability is usually defined as 1 minus the probability of outage. One can also think about that as the fraction of time for which the link is available. Integrity is usually cast in terms of frame error ratio, bit error ratio, and latencies associated with various messages. We see these terms in cellular, Wi-Fi, and so on. Well, ultimately, if the link is not available, the transaction cannot be completed. And I'm focusing here on availability. For any link to be reliable, it must first be available. I'm also going to focus on communication link performance and not on the actions of the aircraft or pilot or airspace operations and reactions to various events. That is how the airspace system reacts to an outage or reacts to an unavailable situation of a link. This graphic, taken from the RTCA MOPS, illustrates classic link availability. In the top, you have this rectangular wave, which indicates that the link is available A or the link is not available, A bar, a binary random process, so to speak. In the line below, the two green blocks denote information exchanges, i.e. that are successful. They take place during the time that the link is available. The yellow fails because the link is unavailable for part of the message transfer, so the entire message does not get through. And the two red information exchanges do not get through because the link is entirely unavailable for the full expiration time, ET, or the link is available at the beginning and then becomes unavailable during the transmission. This table is taken from one of my references. I have a list of references at the end by Klugel and his colleagues. And it lists a number of different applications, data rates, end-to-end latencies, and communications reliability. This is actually a pretty good paper that attempts to translate air traffic management and expiration time and transaction completion into more conventional requirements that we communications engineers often use, such as data rate and latency. You can see that for some of these, the data rate's pretty low, 20 kilobits, 30 kilobits. Some of the rates get pretty high, tens of megabits, and reliability numbers are very high. That is 5 nines, we call it, or 6 nines. In 3 of the center rows there, these are applications described by the authors of the paper for which reliability numbers have not yet been completed, so they just list them as high and medium. Nonetheless, 5 nines is a pretty high percentage, 6 nines, a very, very reliable link. And again, these specifications are still being determined by the various standards organizations. Okay, a bit on AAM links. How many links do we need? How many are there going to be? The graphic illustrates some of those. We expect most of these aircraft to interact with traditional air traffic control. This is done in the VHF band with 25 kilohertz or sometimes 8.33 kilohertz channels using analog modulation for voice, or VHF data link, VDL, which provides about 30 kilobits per second. Fleet and PSU stands for Primary Service Provider for UAM services. Coordination with the FAA for airspace regulations, and air-to-air or V2V links for DAA, which stands for Detect and Avoid. As these aircraft travel at low altitudes and in congested areas, that is high traffic density areas, Detect and Avoid is critical for safety. I list at the bottom there some potential frequency bands that may be used. These are currently aviation bands. Cellular bands may also be used. This is also to be determined. Well, what can we say about this at the physical layer? The velocities of these aircraft are probably going to be less than 100 meters per second, far below that of cruising jet velocities, but greater than automobile velocities. Most of the links will have a strong line of sight component, that is a line of sight, optical line of sight path, or a radio line of sight path between the ground station and the aircraft. There will be a need for air-to-air and air-to-ground. Link range is going to be pretty short, typically, a few tens of kilometers, and at vertiports, which are basically airports on building roofs in urban environments, the range will be pretty small, a few tens of meters, perhaps. For C2, that is command and control, we expect to need some ultra-reliable links, possibly some LL, which stands for low latency. URLLC is ultra-reliable low latency communications, which was introduced by 5G for certain applications. And once again, I mentioned the different frequency bands that may be used in AAM. If we consider the aircraft itself, there will likely be only limited opportunity for MIMO, which stands for multiple input, multiple output antennas, which can provide increases in capacity as well as reliability. There are lots of antennas on traditional aircraft, and adding a new antenna is a difficult thing to do. It has to go through a rigorous certification program and get authorization from the FAA here in the United States. And this is strongly cost-driven. Using MIMO in line-of-sight channels requires beam steering or tuning, and so it's a challenge to do that. In the L and C band, which are likely to be used for some of these communications, we can model the channel as a so-called two-ray channel some of the time, which means the channel consists of a line-of-sight component and a surface reflection. Or when there are large obstacles, terrain, buildings that reflect signals, we may have an N-ray channel with multipath components. The delay spreads, which are the spread of the channel impulse response in the delay domain, have a large range compared to terrestrial cellular. It can be very small, down to a few tens of nanoseconds for a line of sight case, up to a few microseconds, a factor of 100 larger. Doppler, based on the velocity, can be estimated to be less than that, 333 times the frequency in gigahertz. And the presence of large obstructions for these low altitude aircraft will probably imply that we need multiple links for connectivity, multiple bands, multiple links to multiple ground stations, and so on. Well, UAS and AAM are being studied by the 3GPP, the Cellular Consortium. They're being studied by European aviation organizations and around the world. I've just shown a few here. Once again, URLLC stands for Ultra Reliable Low Latency Communications, which the cellular community has developed. All right. Fundamental features of aviation communications and challenges. Well, one, differing generally from terrestrial, is altitude. With an aircraft at altitude, we have a larger probability of having a line of sight path as the elevation angle increases. And this means a smaller path loss or smaller attenuation than in a non-line of sight or obstructed channels. That's a good thing. However, we trade that for propagation of interference. Interference will propagate long distances in these line of sight channels. We also have higher mobility, which gives us increased range, which can be a good thing, but it also gives us larger Doppler shifts, which need to be accommodated in transmitters and receivers for reliable communication. We also need accurate navigation and surveillance when there are a number of aircraft in the vicinity, as shown in the graphic there. Hence, air traffic management is required. Comparing with terrestrial, I'm not going to go through this entire table. This is a qualitative comparison of characteristics of terrestrial and air-to-ground communications. Velocities I've already mentioned, typical small values for terrestrial, even at highway speeds, but for air-to-ground communications, velocities and hence Doppler shifts can be very large. Mobility management is well established for cellular, handoffs, backhaul links to the network, and so on. And this is also well established for passenger aircraft, typically via pilot-to-air traffic control communications and ground-to-ground links between controllers and between ground stations. But it's really to be defined for UAVs. We expect it to be based on similar principles, but it's not defined for these low-altitude aircraft. The primary physical layer impediments to reliability include the wireless channel itself. We have multipath components that cause fading and distortion. We have obstructions that reduce the signal strength at the receiver. We also have interference. Interference can be unintentional, that is within a system or external to the system, spurious emission, but we may also have intentional interference, which is usually termed jamming. I'm focusing on the physical layer, but higher layers can improve reliability as well, as listed below. We can do a format check on the received packet. We can detect collisions of packets from multiple transmitting sources. ARQ stands for automatic repeat request, where we can resend the message. The receiver can tell the transmitter that it only received part of the message or none of the message, and so retransmissions can be affected at the higher layer. We can also do routing at the network layer. That is a different path from transmitter to intended receiver, maybe a relay or maybe several relays. We can also detect errors at the transport layer. All of this takes a little more time typically than the physical layer, but it does augment reliability and will be used. The channel itself, for any communications, any wireless signaling, be it for surveillance or radar or whatever, a physical channel is required. And this is often the most challenging impediment to reliable communications. The simplest channel model is shown there. The transmitted signal incurs both a delay and an attenuation. And as I note, if the physical layer does not work, the remaining layers of the protocol stack don't matter. Even if you're rerouting around a failed link, you need the physical layers of the other links you're using to be up and running reliably. When we look at the channel and compare to terrestrial, aeronautical channels typically have delay spreads that range over a very large range, that is nearly 2 orders of magnitude, whereas for terrestrial cellular, especially nowadays with cell size being very small, have very small delay spreads. Stationarity distance is a statistical measure of how large in space the channel statistics remain approximately constant. It's typically pretty small for cellular, can be large in the aeronautical case if we have a line of sight component. And again, Doppler spreads are small for cellular. People, pedestrians, even cars don't move nearly as fast as aircraft do. So we have to account for that. This slide shows one of the few equations I have in the presentation. It's for the complex baseband channel impulse response, which is illustrated versus time and delay in the lower left graph. So if one thinks about hypothetical impulses being input every so many seconds, those are the gray spikes there at the far left. The channel output consists of additional components, reflections, multipath components, maybe multiple reflections or diffracted components. And these change in time and delay, and we need to understand those changes so that we can design reliable links. I also have some Doppler shift examples there for 2 different frequency bands and different velocities. The graphic on the lower right shows some Doppler power spectra from a paper that some colleagues and I did a few years ago. Well, the channel is varying. 2 examples here. These are from measurements I've done in NASA programs in the past. These are showing power versus delay and distance. They're called power delay profiles, which is basically that channel impulse response magnitude squared. How much power do we get versus delay and versus link distance? On the left, we have a medium aircraft traveling in a hilly suburban environment, and on the right is a drone moving in a suburban environment, going from line of sight to non-line of sight. As you can see on the left upper plot, we have this multipath component that is present for about 150 meters of travel distance. This causes the channel to change quickly if the aircraft velocity is large. Delay spread versus distance is shown in the lower right plot. We have these intermittent multipath components that are rapidly changing and cause a large range of delay spreads. Delay spread is dispersion in the time domain. This causes distortion of the received signal that must be accounted for reliable communications. Some numbers are given there for 2 different aircraft at different altitudes and ranges. And you can see that the mean and max values cover a large range. Another set of diagrams of power delay profiles, power versus delay and link distance for 2 different environments, freshwater and hilly terrain, where the ground station was nearby. This is in Cleveland and Latrobe, Pennsylvania, showing the intermittent multipath components, also showing for 2 different channel bandwidths a different resolution one obtains in the delay domain. The wider the bandwidth, the greater you can resolve these multipath components, identify them. Well, I developed over the years multiple models for these wireless channels, and this is one of them. This is for an overwater channel where the diagram in the upper right shows a tap delay line model. The transmitted signal enters this linear filter. We're modeling the channel as a time-varying linear filter. The line of sight component is the first component with that alpha 0. The ocean surface reflection is the second component. And the third component is what we call the intermittent third ray. This was a multipath component that was intermittent, and we quantified, that's measured data there, the probability of the presence of that third ray for the two cases, the ocean and the freshwater case. And as you can see, in these particular cases, the ground station is onshore, near the coast, and the aircraft is traveling over water, and there are more obstacles to create multipath components nearer the shore, as one expects. However, there are also obstacles on the water itself, boats and oil drilling platforms and so on, that can cause these multipath components. More statistics from the overwater case showing the duration or length of time that the multipath component is present versus distance, and also the delay, the relative delay of these multipath components. There are a number of ways of modeling these channels. We use measurements, but we also use geometry and propagation physics for the two-ray case, and Earth curvature and atmospheric effects are also taken into account. Typically, we model the channel as changing and unknown, so it's random, and therefore we estimate its statistics. And we typically want to know the distance over which the channel statistics are constant. And this has been documented and studied a lot for the terrestrial case as well. And we've taken from our measurements two metrics that quantify the stationarity distance: the temporal PDP correlation coefficient, that's the coefficient of that power delay profile function, and the spatial autocorrelation collinearity, which is applicable for multiple antenna schemes. We use two antennas in these measurements. The results here show the stationarity distance as a function of separation, that's delta x, and link range. The PDP correlation coefficient I'll focus on the left, and you can see that this is sort of quasi-periodic. A larger value of stationarity distance means the channel is stationary, statistically stationary, for a longer duration or a longer period of time. And hence you're able to characterize it and understand it and ameliorate any of these detrimental effects more leisurely, let's say. We found that the median stationarity distance for the overwater case was about 15 meters. And this is, a pretty large distance, although if the aircraft is traveling at 100 meters per second, of course, that's a fraction of a second. Another impairment that we can encounter is airframe shadowing. Now, this is most common with larger aircraft and fixed-wing aircraft, and airframe shadowing means that the aircraft itself is obstructing the line of sight. This particular plot shows received power versus time when the aircraft was making a banking turn and the line of sight component was blocked by a wing. And we found that these fades in both L-band and C-band can exceed 30 dB. And the fading rates are about 15 dB per second here. This was a fairly slow banking turn that we did on purpose to quantify this effect. And we've come up with models for this as well. For smaller aircraft, especially rotorcraft, large shadowing events typically won't occur, but these aircraft do have variation in their pitch, their roll, and their yaw in maneuvering. So we may see some airframe shadowing with smaller aircraft as well. Antenna effects are also important for the link, understanding the channel. Here we illustrate some antenna patterns for an antenna mounted on the bottom of an aircraft. This is for KU band. We did some measurements, again, with NASA a few years ago. The manufacturer provided pattern is shown in the black line on the left. And you can see that NASA measured all these other patterns at different link distances and different altitudes. And they are mostly similar, but they tend to have deeper nulls and more frequent variation than the manufacturer provided antenna pattern does. This has to be accounted for too, because some of these nulls are up to 20 dB in depth. That would look like a fade, a channel fade to the receiver. If an aircraft is flying from behind the antenna's main beam for a directional antenna, as illustrated on the top, it will see the received power increase as it goes into the main beam. And then small scale fading is also occurring here. Knowing these effects enables us to design the link appropriately to account for this fading. I want to mention a brief example for what I call ultra reliable communications. This is just an example with some numbers. Let's say for the command and control link, we have a data rate of 100 kilobits per second, so the bit time is 10 microsecond, and if we're sending a 100-bit packet, the duration of that packet is 1 millisecond. For a small drone flying at about 40 meters per second, we can compute that the distance traveled over the packet duration is only 4 centimeters. But at C-band, that's about 2/3 of a wavelength, so small-scale fading is occurring. Small-scale fading has been quantified for decades. One of the worst conditions, near worst, is called Rayleigh fading, where you have no line of sight component or no dominant component. In that case, for say a 20 dB fade, that occurs about 1% of the time. That's pretty significant. More likely in the air-to-ground case, where you have a line of sight component, we would see what we call Rayleigh fading. We've quantified that as well. The Rayleigh K factor represents the ratio of power in the dominant component to that in the scattered or multipath components. And a fade of 20 dB occurs only about 10 to the minus fifth of the time. So one might ask, do we need a 20 dB margin to account for that? The one answer is yes, we can do that. And that's what current VHF aviation communication systems do. They just transmit at a fixed power level, which is very high, 10 watts, much more than needed most of the time, but they have plenty of margin. It's fairly simple, but it's power inefficient. What else can we do besides margin? Well, we can use antenna diversity, spaced antennas that are spaced a few wavelengths apart. We can use multi-band links because the fading is different in different frequency bands. And we can use what is also called spread spectrum overlay. I'll talk about that shortly. The last thing I want to mention on the air-to-ground channel itself is blockage and obstruction. The plot there shows line of sight probability versus elevation angle when we have a ground station that is pretty much a pedestrian with a height of about 1.5 meters. And the probability of having a line of sight depends on elevation angle. And as one expects, as the elevation angle increases, you're looking up higher, so you have a higher probability. More data needs to be done for this kind of environment with realistic ground station antenna heights and in realistic urban environments. There are some models, mostly geometric, and obviously they ought to be validated with measurements. All right, on to interference, specifically jamming. Most intra-system interference is pretty well managed by frequency assignments and spectral masks. That is, ensuring that the power spectrum doesn't go outside its allocated band. Jamming, however, is when someone intentionally radiates an electromagnetic signal for the purpose of disrupting. Now, the jammer has to do that in the right frequency band, at the right location, and at the right time. And this jamming can disrupt not only communications, but also navigation, surveillance, sensing, any operation that employs electromagnetic signaling. The military has looked at jamming for decades, and it is part of the broader area of what they call electronic warfare, which also includes spoofing, system overloading, and in the case of, say, fighter jets, mechanical jamming to confuse radars, where aircraft throw out metal pieces called chaff to confuse radar. Some settings. Jammers can be airborne, they can be on the ground, they can be both. They can be fixed in space, fixed in time, fixed in frequency, or varying in all of those. The effectiveness of the jammer depends on its transmission power and the propagation environment, and also on the type of signal being jammed and the type of signal doing the jamming. Some basic math. Communication performance, surveillance, navigation as well, depend on the SNIR, signal to noise plus interference ratio. Here, the interference, is the jammer. So SNIR is the received signal power divided by the noise plus jamming power. A diagram in the lower left shows a transmitter and receiver separated by distance d, and the jammer is distance d sub j away from the receiver. If the jammer power is much larger than noise power, the SNIR can be approximated as S over J. which yields that approximation there. So we can deduce that as the jammer power relative to the transmit power goes up, quality of the signal, SNIR, goes down. Similarly, as the ratio of distances, the propagation distance for the transmitter to receiver link divided by the jammer to receiver distance goes up, the SNIR goes down. What kind of signals do jammers use? Well, they can use a noise-like signal, which is fairly easy to generate. It has a high peak to average power ratio, so it's hard to generate very high power, very wideband noise signals. And it's typically spectrally white, but it can be filtered. The most effective jammer will use a signal modulated, or at least spectrally and temporally similar to that of the signal it's trying to jam. This is typically a digital signal, for example, a phase shift keying or frequency shift keying or a QAM signal. Jammers can also frequency hop. They can follow the signal. That is, they can learn the pattern of a signal and repeat it back. So the jammer actually receives the communication signal, amplifies it, maybe does something else to it, but then sends it back to confuse the receiver or create in-band interference. Each jammer type can also be continuous or pulsed. It can be full band. It can be partial band. There's a lot of variety, just like in signaling. How do we mitigate jamming? Spread spectrum is by far the most effective signaling technique to mitigate jamming. That's when you use a larger bandwidth than is required for information transfer. This has been studied for decades as well. It was used in 3G CDMA and is mostly direct sequence and frequency hop, but hybrids are also possible. Other ways to mitigate jamming includes strong coding, interleaving, spatial techniques, nulling and beam steering, and again, procedures at the MAC layer and above. One can also do active interference cancellation, that is, detect the jammer as a signal and then subtract it. This is easiest if the jammer is continuous and deterministic, but not so easy. It's a very challenging signal processing if the jammer is varying its parameters, timing, frequency, spectrum, power, so on. The block diagram indicates or illustrates an interference canceling technique for multi-users in a spread spectrum system. Well, what does jamming do? First of all, it degrades performance. It lowers the SNIR, which gives a larger bit error ratio. It can also, for images, reduce the image quality, cause voice messages to be garbled or unintelligible, and so on. If it's strong enough, it can sever the link, as we say. It causes an outage or a lost link, or disables the synchronization ability of the receiver. In extreme cases, very high power jamming can cause damage to the RF electronics. That's typically when the receiver is very close to the jammer. Here's a simple jamming example. On the right, I show a 10-kilometer flight path where the aircraft is at an altitude of 1 kilometer. Both ground stations transmit at 10 watts with a noise figure on the receiver of 3 dB and 1 megahertz bandwidth signal, and the ground station antenna height is 100 meters. Very high, but possible. The jammer is placed halfway between the first and second ground stations, 5 kilometers along there, but is 1 kilometer great circle distance away from the actual flight path. And it's using only a 1-watt transmitter, and it has a height of 10 meters. For simplicity, I'm assuming omnidirectional antennas, line of sight channels, and the receiver threshold is 5 dB. Now that can vary, but it's a reasonable number when you have error correction coding used. On the left plot, we show the no jammer case, the signal to noise ratio versus flight path distance. The blue line is the SNR from ground station 1, and the orange line is dash line is the SNR from ground station 2, well above threshold. And this is, again, typically what is done today. On the right plot, we show the signal to noise plus jamming ratio when the jammer is on. And as you can see, the minimum SNR reduction from jamming is 15 dB. It goes down at the beginning by at least 15 dB. And as the aircraft gets closer to the jammer, the SNJR goes way down and goes below threshold for approximately 2 kilometers. That is 20% of the link distance. The jammer causes this link to be an outage. And this, again, is a very simple example using straightforward link budget equations and geometry, but it illustrates that a simple jammer at a fairly low power compared to the transmit signal can be very detrimental. to aircraft reliability. Transmission security is something that network people and the military talk about. The idea here is to protect transmissions from interception and exploitations. There are spatial techniques, antenna nulling, temporal techniques, frequency domain techniques, spread spectrum, low probability detection signaling, which is not going to be used in aviation because we want a high probability of detection for receivers. Anti-jam signaling is also used. Exploitation means that the adversary can use the information for other purposes like geolocating and estimating the movement or intent. This too is not necessarily critical for AAM. Well, navigation and surveillance are also operations that use wireless signaling. So the same principles and techniques as used in communications apply. For reliable communications, you need a minimum SNIR. GPS jamming has been fairly common in aviation these days. As far as surveillance goes, commercial aircraft today use ADS-B, Automatic Dependent Surveillance Broadcast, which works in a known frequency band in a 1 megahertz bandwidth. And AAM is likely to use this, but it may need more spectrum because this 1 megahertz of bandwidth, which is shared over in a time domain fashion, can only support a given number of aircraft. So there may be new air-to-air links required for this surveillance or detect and avoid DAA. Well, if we consider the adversary's perspective, how might we effectively disrupt a link? I don't want to provide a lot of information here, which is why I blocked this out. But the first point is a lot of this information is public, like cellular standards. So we can, the jammer or adversary can learn the frequency band, transmission power levels, modulation schemes, flight paths, and so on. And an effective or smart adversary will come up with some sort of strategy as to where to do the jamming, how long to jam, what kind of equipment it needs, what kind of signaling it needs, how long should it be on to avoid detection itself by authorities. Once again, the military has studied this a lot. Well, what can we do to make our link more reliable? What countermeasures can we use? I've already mentioned some of these. For channel effects, such as multipath, we can use frequency diversity, we can use spatial diversity, power control, which require some complexity increase over existing radios and a cost increase, but this is a mature technology. For shadowing, we can use time diversity, site diversity, likewise, some cost involved there, and also a little bit on latency and capacity. To be reliable in the presence of jamming is going to require additional cost and complexity. We can implement spread spectrum and power control, multi-band communication, for example, transmitting in widely separated bands. And we can also, if we like, use more sophisticated techniques such as adaptive directional antennas and interference canceling. Interference canceling is being used in cellular today for what they call NOMA, non-orthogonal multiple access. Signal processing techniques are mature enough that consumer devices can do this, but doing it in aircraft radios requires a higher level of sophistication. Okay, I'm nearly complete, but I wanted to talk a little bit about future work. First would be to quantify the costs of a link disruption, doing a risk analysis. How long can an outage last before we decide it's intolerable? In that jamming example I did, is 20% of the link distance 2 kilometers of outage okay? Can we just deal with that? Or do we need to do something? What are the costs? Quantify what it would take to use multi-band links. People are looking at this a lot. Which frequency bands do we use? What are the data rates and how do we balance and so on? Also quantify the benefits of spread spectrum. How would we introduce that? One easy way is to take existing FDM links, which are channels, aviation links are given frequency channels, oops. And we could frequency hop them, but that would have to be coordinated. Obviously, if we're introducing any new radio air interface, we need to test it. And as the military calls it, red team testing. We should actually have people on our own side test the system to disruption and ensure that we have not overlooked any vulnerabilities. Okay, now I'd like to summarize what I've talked about today. Aviation is growing, particularly for UAS and AAM, which was a focus of this talk. There are multiple programs worldwide going on to introduce advanced air mobility into areas that have traditionally not been served by aviation, urban and regional and so on. Air traffic management, when you have more than a few aircraft in the space, requires reliable air-to-ground and air-to-air communications, communication, networking, navigation, and surveillance, as I term it. Link availability underlies reliability, and reliable signaling underlies reliable networking. And what I mean by reliable signaling is signaling reliably at the physical and lower layers. The URLLC, ultra reliable low latency communications, may offer from cellular, may offer us some tools. They've done some studies on this and have affected some nice ways to achieve this for cellular communications that we may be able to borrow. In addition, reliable signaling requires that we understand the physical channel, because the channel, the air-to-ground channel in particular, can be rapidly time varying, it can have large Doppler, and it can have a large range of dispersion, delay dispersion that can cause distortion. We also need to realistically characterize what our adversary may be. Now, we are not expecting to operate this in a military conflict setting, but aviation communications has been jammed in the future. People have been caught doing it, caught jamming. But if there is an adversary that we want to guard against, we need to take into account what that adversary may do, what public knowledge they'll use to create an impairment. I provided some example results of the channel impairments and jamming. In particular, the air-to-ground and air-to-air channels can yield small-scale fading, obstruction, and rapid time variation, all of which need to be taken into account. And we do understand how to do this for the most part. These techniques have been matured over decades. Likewise, interference or jamming can yield a reduced signal-to-noise ratio, or in some cases, a link outage, which gives us zero availability for some time duration in some region of space. Thus, this makes always available or reliable CNS for AAM quite challenging. And I recommended that we investigate new designs with multiple frequency bands, possibly antenna techniques, possibly spread spectrum techniques. And that concludes my talk. Thank you. Okay.
Hello.
Yes. Yes.
Okay. Yeah, I was going to use this awkward silence to or fill it in with the question. So yeah, my name is Evgeny Vinogradov, and I was working a lot on channel modeling, and for the last couple of years also on UAV channel modeling and on the communication systems in general. You mentioned ADS-B as a potential candidate for exchanging messages between aircrafts, also in AAM and UAM.
Yes.
Well, also NASA has shown that it's causing quite significant interference to the manned aviation, so they do not really like the idea as far as I understood. What would be the alternative? I don't know, would be something like remote ID, remote identification be an alternative way of doing the same thing, but for drones and for air taxis and other vehicles of that kind?
Yes, good question. I think the interference to existing aviation systems is primarily because they're using it in a frequency band where aviation communications takes place, right? So one way to do it would be to move to a different frequency band and still use it. Remote ID still has to get the information out there. And if there are not dedicated frequency bands, spatially allocated, then interference will still be a problem. I haven't actually spent as much time studying DAA and surveillance. My colleague Kamesh probably knows more about that than I do for the air-to-air link. But yeah, the remote ID is the aircraft is required to broadcast its identification and possibly other information like intent, that is velocity and trajectory information, which is what ADS-B calls as well. And you're right, ADS-B has limited capacity, which I think I mentioned here. As the number of aircraft in a given area grows, ADS-B will saturate, and we need either additional frequency bands or a more efficient technology to affect that information transfer reliably.
Thank you very much.
Thank you.
So just to add, this is Kamesh. The FAA is looking for to come up with a frequency band, and I believe it has requested for information for using 5 gigahertz band again for drone-to-drone communication, but nothing is set in stone yet.
Thank you, Kamesh. Yeah, the 5 gigahertz band has been unused over the past 50 years, or I should say underused. And so that is a primary band for a lot of these new services. I see a question in the chat. What FEC would be most recommended to mitigate adverse issues? FEC is a pretty mature technology, forward error correction coding. I believe that the LDAC system, which is an L-band digital aviation communications, which is being standardized in ICAO, uses a combination, a concatenated code, Reed-Solomon and convolutional. Now, that's very traditional. It's very effective, but it's not as effective as, say, low-density parity check codes, which are used by cellular and Wi-Fi, and also polar codes, which are fairly new, that are being developed for cellular as well. Polar codes are probably the best candidate because they are codes that can achieve near capacity performance. Interleaving is also good. Typically, some of these codes require interleavers, some do not.
May I use an opportunity for another question?
Sure.
Yeah, you mentioned also ICAO, I'm not sure how to pronounce it correctly, but in their UTM framework, they highlighted that cellular communication is going to be probably the primary candidate for air-to-ground communication and maybe for air-to-air. I don't know what they meant, maybe side link or something like this. But you somehow did not dedicate that much time to cellular communication directly.
Correct. I think cellular has a role to play. Of course, cellular companies are happy to provide the service, right? It's going to cut into their capacity unless they take measures to ameliorate that. So they'll have to have upward tilted antennas, for example. Initial experiments that I've read about show that using the same frequency bands as cellular does cause a lot of interference, and they have to manage that. And so I think the aviation community is happy to have the cellular communications community help, because the aviation community doesn't do high-speed networking, right? They have radars and ground stations and ground-to-ground communications between air route traffic control centers, but the coordination is fairly slow. We need faster coordination. So I think cellular will be a part of this. I think there are many in the aviation community who are still a little bit skeptical that they can provide the reliability, right? Cell phones, we have drop calls, not as much as we used to, but we still have those. Incurring that in an aviation environment, especially when you have many aircraft at low altitude in an urban environment, is going to be more challenging. So I think the reliability numbers are maybe one of the biggest challenges for cellular. But good point. The cellular industry will be involved with this.
And could you please share those references that you mentioned, Luke?
Oh yeah, I think the slides will be made available. Is that correct, Kamesh?
Because the reliability
Yes,
issue.
they will be made available.
Yeah, I
In
have
fact,
a few pages of references here that will be made. Yeah, the presentation should be made available.
Perfect. Thank you.
Welcome. Thanks, Katie.
Thanks. Yeah. I believe we can wrap up. I believe if there are no other questions.
All right.
There are few slides, David. I think at the end we wanted to once again invite all the students. I mean, all the people, all the participants to continue engaging in this webinar series, and also we would like you to join if you are not a member of VTS. There are many conferences and many opportunities in terms of learning, and especially for students. So with that, we will be wrapping up this webinar, and look forward to seeing you again in the next month. And thank you, Professor Metalog, for taking time to share this knowledge and your expertise, especially in this for this topic. Thank you.
Thank you.